Hello, and welcome to our third meetup. We kick off this year's first event with very special guests today. And before we start, we just want to take this opportunity to thank Naptif, our main sponsors for the Cloud App Developers community, as well as all of you who have joined us today. We want to remind you that you can stay up to date on any news and upcoming events by joining our Substack at cloudappdevelopers.substack.com. Now, without further ado, let me introduce to you our first speaker, Abdel Sghiouar. Hello, Abdel.
Hello.
Yes, we are live now. Now, Abdel is a senior engineer at Google, as well as one of the hosts of the Kubernetes podcast. And today he's going to talk to you about how to secure your software supply chain from dependencies to deployments. Abdel will make sure he answers any questions that you have at the end of his talk. So make sure you can write them in our chat during at the YouTube channel. So Abdel, without further ado, you can take it from here.
Thank you. Let me just go ahead and share my screen. I think I'm going to share my whole window. Hopefully you can see at least my slides for now. Yep. I think we are good. All right. So hello, everyone. Thank you for having me. I'm going to talk to you today about like a word or a term that have been circulating in the cloud space over the last few months, I would say about a year. And that's something we call software supply chain security, or SDLC. It is kind of a new terminology that just started bubbling up recently due to certain events, and I'm going to talk about these events as well. But like the purpose really of this talk is to be showing more practically how this thing looks like, right? Not really just talk about the theory behind it. I'm going to explain a little bit the theory, but the main goal is to show the practical part. I have two demos, if everything goes well. One demo is actually using open source stuff to do software security at runtime. And then another demo which shows the entire life cycle from the development side all the way until the production side, including CI/CD, etc. And that one uses mostly our technologies, but they are actually based on open source. So I'm going to be using the Google Cloud Console most often, but that doesn't mean that all this stuff I'm going to talk about are not applicable anywhere else. The concepts remain the same. The implementation detail might vary depending on which platform they run on. But generally speaking, it's the same stuff, right? It's all open source. So yeah, my name is Abdel. I'm a cloud developer advocate at Google. I'm also the Kubernetes podcast co-host. If you are a listener, hi, and that's my Twitter. My background is in software engineering, but I've been mostly working on infrastructure and on container-related topics in the last few years. So that's kind of my main area of focus right now. And so, like answering the question of before answering the question of what is software supply chain security, we have to answer the question of why this matters and why people even came up with the term to describe this set of practices and set of tooling that ensure security for software through the supply chain. Just for you to understand something, supply chain here is used in the context of the actual supply chain that brings food to your table, which in a very high level, you can think about it as the various steps food has to go through from production. So from the food is being grown to when it makes it to your table. And the analogy here is that the place where food grown is the development phase, the food being put on your table is the runtime or the consumption or the production place. And in order to get the food from place A to place B, that's what we call a supply chain, and the supply chain could be vulnerable at multiple steps because each time food is changing hands between people. And so the analogy came from the supply chain world, which doesn't always, of course, apply to food. It applies to anything, but the similarities with the way we ship software are quite I would say quite striking or quite close. So generally speaking, you as a developer, you write some sort of code, right? Which pulls a bunch of dependencies from the internet. And this is probably something you don't think about too much, or you only think about it when your dependencies break somehow. But where those dependencies come from and what is the source that you are pulling these dependencies from matters. and again, it's something that we have been thinking about it as an afterthought, or maybe not even thinking about it. And so usually you write your own code, you put your dependencies, you put all of that stuff through like a build system, and then you package your application and you run it. And just from this first diagram, you can see that actually like supplying software to production is a set of steps, which is very similar to supply chain, right? Now, your dependencies themselves are developed by somebody else who have a similar sort of set of steps to get dependencies from the developer laptop into hosted in some sort of dependencies repository that you can pull from, right? And the complexity of this set of steps or this supply chain have proved to be extremely interesting for bad actors, because in the past, what hackers or what bad actors would do is that they will try to attack your runtime. They will try to go after your server, after your production system. They try to find a way, find a backdoor, find like a workaround, find like a wrongly published credential somewhere, and use that to access your system. But it turns out that there is a different way, which is if I, as a bad actor, can actually provide that backdoor early in the supply chain and just wait until that backdoor makes it into the actual production system, then I can take advantage of the backdoor. So some of these, like some numbers you see here, like Sonatype is a company that does software security tooling. They predicted that in 2021, they predicted that like open source supply chain attacks will increase by 650%, or have increased by 650%. 81% of commercial software commercial code is based on open source software, which has vulnerabilities. Now, I'm going to stop here and show you a very good example that happened in Sweden. So last year in Sweden, one of the very popular supermarkets got actually hacked. And the reason they got hacked is because they use a software called Kaseya, or they use a software by a company called Kaseya. Kaseya is like a monitoring company, and they use their software, and somebody in Kaseya pulled a dependency which had a vulnerability, which had a backdoor. They pulled it, they packaged it as their code, they distributed into their client or to their clients, and this supermarket was one of them. They pulled that software, they deployed it everywhere, and they had a backdoor running for a few months before they realized that, right? And so just from this example, you can already see that being able to inject things, inject like vulnerabilities or inject backdoors in software early in the development phase could be a very good strategy for bad actors. Another number, like Gartner 2021, in one of the reports, they said that 45% of the worldwide organizations will experience an attack on their software supply chain by 2025. And so what does that mean, actually? Well, let's break down this software supply chain that we talked about, and let's see at each step where can things go wrong. So starting with the injecting bad code. So that's basically bad actors purposely and on purpose injecting backdoors or bad code into dependence into your code. So that could be internal actors. It could be like your own employees trying to sabotage the company, which happens. It could be, somebody stole your developer laptop and then they stole the code, and suddenly they have credentials of that developer. They can start committing code as if the developer is doing that work, right? Then somebody could simply compromise your source control. This could happen. One of the most popular managed CI tools recently had a breach over the Christmas last year, and some code or some credentials leaked to the internet, and some of those credentials were actually access keys for GitHub repositories or SSH keys for GitHub repositories. So you could accidentally leak your own access credentials for your source control, or you could be trusting somebody who doesn't handle them well, and then you end up with your credentials being leaked into the internet. So somebody could actually technically modify your code between it going from the source to the build system, right? Then at the build system, again, same thing. Somebody can compromise the build system and change how your CI/CD pipeline works. you could get compromised by pulling vulnerable dependencies, right? This is one of the most common examples that I can give is a few years back, a developer, like a researcher, a security researcher, managed to prove that they could easily get access as a committer toward, or as a maintainer, toward the GitHub repository of Homebrew, which is the popular software Mac users use to deploy things, right? So that researcher was kind of wearing a white hat, just trying to demonstrate how easy it is, and they managed effectively to get maintainer access. When you are a maintainer on the GitHub repository, if you do not have branch protection, for example, on the main branch, then pretty much anybody with their maintainer role can commit code to the main branch. That is one of the reasons why, if you have a GitHub repository, your main branch should have some sort of protections, like no one can commit code unless it's reviewed by 2 people, or no one can commit code unless it passes some sort of test or something like that, right? Then the packaging comes the packaging. Also, the packaging can be compromised, right? Same way that your build system can be compromised. Or the thing that deploys your application can be compromised. And actually, one of the typical bad practices we see going between build and runtime is often people will just rebuild the apps. So you essentially take source code written by your developers, dependencies, you pull them together into the build system, you build an artifact, and instead of just using the same exact artifact all the way until production, when you come to the packaging, you just rebuild it. And when you come to deployment, you rebuild it. And maybe when you come to the QA, you rebuild it. And that's really bad practice. If you have a CI pipeline or CI/CD pipeline, the same artifact that was built and tested should be the exact same artifact that should end up being deployed in production. Because if you rebuild your code between the steps in your CI/CD pipeline, you risk all of this stuff. You risk just somehow pulling a vulnerability which was not known before, and now it's known, or like pulling a new version of some sort of library that had vulnerability or something like that. So, in a nutshell, this is what software supply chain security is about. It's about looking at the way we deliver software to production as a set of steps, that each step could have a specific attack vector, and trying to fix that specific attack vector. And this whole software supply chains SDLC started a movement that we now refer to as the shift left movement and the zero trust movement. So shift left and zero trust are 2 different things, and I'm going to explain each of them separately. Starting with shift left is very simple. The shift left movement basically means let's put the responsibility of security early in the development stage. Let's make developers not responsible, but aware and accountable for security, and not by shaming developers and telling them that they don't know what they're doing, but rather by equipping them with tools that can allow them to actually know if the stuff they are building and shipping are vulnerable, right? That could be as simple as giving them vulnerability scanners, right? So they can build their software, and then immediately the build system can tell them if there is something vulnerable in their artifact. And then the same thing goes for the spline and the build pipeline. But the whole idea is that the shift left movement says, instead of focusing our security efforts only on the runtime, we will spread it and we will have it through a set of steps, right? The second one is zero trust, and zero trust can mean various things in various contexts. But in this specific context, in the context of security, the zero trust means basically that we have to find a way to establish trust between development, supply, and build to runtime. And we can do that through multiple things. I'm going to demo one way to do it, which is basically signing images. That's as simple as immediately after you build an image, you sign it, and then you verify the signature along the way that you are testing and shipping your artifact to production. And this whole thing started, I would say, like a combined effort of multiple companies called Sghiouar. So Sghiouar is like a consortium, which is tasked by doing 2 things: creating a set of tools and creating a set of frameworks. Talking about the frameworks first, they came up with a framework called SALSA, which stand for Software Lifecycle Security Artifact, or Secure Artifacts, I think, which essentially is a set of practices that a software supply chain security pipeline has to follow in order to assure certain level of security. So there are 4 levels, 1, 2, 3, 4, and basically there are few set of requirements that your supply chain system has to follow in order to meet one of those levels, right? And I'm going to talk about this a little bit more in detail, but I want to start with showing you the open source stuff they do. They do a lot of open source things: Cosine, Recore, FuelShield, Trustroot. One of my favorite is Cosine, which is the demo I'm going to do right now. So Cosine, what it is essentially a command line tool that allows you to sign a container image and make sure, and then there is an accompaniment system that allows you to make sure that what's deployed is the thing that have been signed. I'm going to switch to my... oh, sorry. I realize I am actually sharing the wrong screen. Give me a second. I will just share my entire screen up. Here we go. Ah, right. Now it's good. Now if I switch here and try to go a little bit big. I'm not sure how well you can see my terminal. If you cannot see it, please just let me know in chat and I can zoom in more. So here we go. So I have, let's start with what I have, what I'm trying to achieve and what I'm trying to do. So I have a Google Cloud project here. I'm going to show you here. I have a Google Cloud project which has a Kubernetes cluster running in it. Nothing to zoom in would be helpful. Okay, I'll zoom in a little bit more. But let me start by this. So I have a GK cluster, just a Kubernetes cluster. By the way, this thing that I'm showing, Cosine, can work on any environment. It doesn't have to be Google Cloud. It's open source. So it's just a standard Kubernetes cluster. And I'm going to show something. So let's start with zooming in here a little bit more. All right, I hope that this is good. On my small screen, it looks very good, so I assume it's going to be good. So I have configured my cluster. I have nothing running on it for now. It's empty. Well, sorry, I lied. Let me delete this one. qtl delete, I think deploy nginx. Okay, so I will deploy something, right? I'm going to run a command line, and I'm going to tell you what's wrong with my command line. So I'm just going to do this. Boom. So for those of you who are not familiar with Kubernetes, don't worry too much if you don't understand it. But basically what I'm doing is I'm creating a deployment called nginx, and I'm pulling an image called nginx. If I do this, in theory, it should just work. If I try to see what I have deployed, well, I have a container running there. So typically when I do this in front of a live audience, I pause and ask them, what do you think is wrong with this? But because we're online and probably comments will take time to come through, I'm going to explain to you what's wrong with this. Basically, the default behavior for Kubernetes, when you deploy something and you don't specify the image with an URL, you just say the name of an image, it will default to pulling the image from Docker Hub. Now, Docker Hub is a registry which has a free part of it and there is a private part of it. This will basically pull the default nginx image, which is under dockerhub.io/nginx, whatever that image is. This is a problem because essentially I deployed an nginx image into my cluster, which I don't know where it's coming from, right? So how do we solve this? Well, there are a few ways we could do it. Delete deploy. So I'm just going to delete my deployments because I don't think it's safe to leave it in there. There are multiple ways you could solve this. You can go the hardcore way, which is you lock down your Kubernetes cluster, you lock down your environment, you host your own images, and then you only allow your own images to be deployed. That's one way to do it. The second way, which I think, in my opinion, is much better, is to use Cosine to sign the image. And again, here I'm going to use Cosine to sign an image which I'm pulling from the internet, which is sort of opposite to what I'm trying to advocate for, but you will understand the point. So what is Cosine? Cosine is essentially a command line that takes an image, an artifact, and then it takes a key, a public key, and then it uses the key to sign the artifact, generate a signature, and store it with the image itself, right? So again, without going too much into details, I have a key here, which is stored on KMS, key management system. That's like a Google managed key management system. It's just like an asymmetric sign-in key. So it's a public private key, which is protected by software. Again, the key that you use to sign image with cosign could be anywhere. It could be on Google Cloud, Azure, AWS, or it could be a self-generated key. It doesn't matter. It's just like a asymmetric key, right? So what I'm going to do is I'm going to pull the image. I'm going to pull the Docker Nginx image. Again, I'm pulling from the internet. This is not what you're supposed to be doing. You're supposed to be using your own image you built yourself, right? So consider this is a replacement of you building your own image. Now the real stuff starts from here. I'm going to tag my image so I can push it to my repository. So sorry about that. Without going too much into details, this basically just puts a tag on the image so I can push it to a container registry. Then I'm going to push the image to the container registry, and I'm going to do what I'm going to do is I'm going to pull the SHA, so the unique hash for that specific image. So this is going to push the image and then pull its unique tag, right? So I'm going to wait for a moment. So here we go. I have my, if I just echo my SHA, this is my SHA, right? Now I'm going to go back and show you where that image is very quick. So if I go to my container registry here, I just have an artifact registry. It's just a remote place where I have an Nginx image stored there, right? If I click on it, there is only one image. And if I look at the manifest, it's just a Docker image, right? Now, what I'm going to do is I'm going to use cosign to sign that image. So the way cosign works is this. So cosign sign, I have to give it a key. So I'm using the key that I created earlier. And this is my container image, right? Using the SHA that I pulled earlier. So I'm going to go ahead and do that. So what this thing will do, it will take the image, it will sign it. It will not take the Nginx image. It will take the specific Nginx image, which has this specific tag. It will sign it, and then it will push the signature as metadata to the image itself. So if I go back here 1 second and just refresh this page, I can already see that I have an extra piece of artifact. So my image is Nginx, and it contains two things. This here in the bottom is the image itself. Here is the signature. So if I look at the manifests, I can see here that I have my signature. So this is the unique signature that identifies this specific image with this specific digest, right? If I would change code, if I am in a development environment and I'm just changing code constantly, this signature will be different if I change code. Now, I can verify the image. So this is basically signing the image at the development phase, right? Obviously, in production, you're not going to be doing this manually. You're going to be doing this as part of your CI pipeline, which is build the image and then sign it. Now, what I can do is I can also verify the signature using cosign again. So just rerunning cosign here, I can see that, okay, my image have been validated and the signature have been validated against the public key. So my image is signed. This is part of the, so the signature is establishing the trust, verifying is verifying the trust. Now, next step is I want to make sure that my cluster, my Kubernetes environment can only accept images that have been signed, right? So how do I do that? Well, the cosign people, they created what we call an admission controller. Again, without going too much into details, if you don't understand what Kubernetes is, it's essentially a gateway, a keeper, a thing that will verify that my image is signed before it allows it to be deployed. And so the way I configure it is I create this object called cluster image policy. And basically I say this applies to all the images, and the key against which the verification has to happen is this one, right? Then boom, that will create my policy in the cluster. Then the next step that I have to do is I will just create like a test namespace just for the sake of demo. And then I have to create a tag. And the tag is essentially policy.sigstore.dev include through. This essentially tells the admission controller, this namespace is the policy I created earlier applies to this namespace. Now, let's try what I did earlier again. I'm going to just try to deploy a random image pulled from the internet. kubectl create deployment Nginx, the image is Nginx in the namespace test. This in theory should fail, right? Because there is a policy and the controller verified the image against the policy and said, okay, well, this image is not signed, so I cannot allow it to be deployed. So I'm just going to go ahead and now deploy the actual image I showed you earlier, with the actual tag, and this should normally go through, right? So this is allowed. Now, this is sort of only specific to Kubernetes, because the controller is a Kubernetes concept. Even if the command line is not, the command line can be used to sign any image, any container image. It wouldn't work for jar files. It wouldn't work for npm packages. But the whole point of this demo is just to give you an idea about what do we mean by established trust. So we build an image, and at the build time, we sign it, we attach the signature as the metadata, and then we can verify that signature through the entire supply chain, right? I think I can take questions later. Let me just carry on, and I'll take questions later. So this is the demo for what we mean by the shift left movement, right? Shifting part of the security aspects, part of the establishing trust to left, which means to the build system or early on. Now, what we did at Google is we took all of these things, basically the salsa stuff that I showed you earlier, the kind of frameworks, and then the tools that exist, and we created something called the software delivery shield. What is the software delivery shield? It is essentially a set of tools that allows you to secure your supply chain on Google Cloud, from development to build. And that essentially includes from the development phase to the supply phase, to the CI/CD, to the runtime. And I'm going to explain what each of those are. Starting with development, we launched something called Cloud Workstations. So what Cloud Workstations are, they are managed development workstations, Linux-based, that allow you to keep your code in the browser, in the cloud. When you use this, you are developing in the web. You are not cloning code locally. Everything stays in cloud. Now, I know that whenever I bring this topic, there is usually very loud voices with people with very big opinions saying, no, but I don't like to write code in the web. That's stupid. What if blah, blah, insert reason. So what have happened in the meanwhile is that JetBrains have released something called JetBrains Gateway. I unfortunately don't have the licenses for a JetBrains IDE, but I'm just going to show you what the idea is. What the gateway essentially is, it's a client. You can see I launched it. This is a Mac app. And unfortunately, I cannot zoom in. But essentially, this is just a client that I can actually use to connect to Google Cloud. So I can click on it, and I have configured it already. It have detected all the workstations I have in my project, and I can click next, 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 next. I'm not going to do it because I don't have the licenses, but the idea here is that I can use a local client and connect to a remote IDE, so that the backend for the IDE is in the cloud, but the client is local. And this client works on Mac, works on Windows, works on Linux. So the idea here is that with JetBrains, you get the same look and feel of your local IDE, except that none of the code and none of the data is actually stored in your local laptop. It's all remote, right? So that's Cloud Workstations. And with Cloud Workstations, if you have noticed something, it does kind of look like Visual Code, right? That's the default mode. It's actually Visual Code if you don't change the kind of IDE. It comes with Cloud Code Source Protect, which is a plugin that you can actually deploy into Visual Code if you want, but it's pre-deployed on Cloud Workstations. And essentially what it does is that it scans your dependencies. So it looks at your pom.xml or your requirements.txt or your packages.json, and it just scans those dependencies and show you in the browser if you have any CVEs. So this is part of what we call like enabling developers to know if they're using the wrong or vulnerable software, right? Then we go into the vulnerability stuff. So we have built-in scanners into our registry. So if you push your images to container registry or to artifacts registry, then we will continuously scan them and highlight CVEs, vulnerabilities. We also have something called assured open source software. This is still in beta, but essentially what it is we are going to put up, we put up a repository which contains 250 plus of the most common Java and Python packages that have been tested and that are guaranteed to not have like critical vulnerabilities in them. And so you will essentially, instead of pulling Java and Python from Maven and any other place you pull Python packages from, you will pull them from us, right? That's essentially what assured open source is. Then what we did also is we built this Salsa 3 compliance into our CI, which is Cloud Build, and we have it built into the console. I'm going to show you a demo later. We also have something for runtime. So Cloud Workstations is development phase. I talked about the CI/CD phase, the supply phase, and now the runtime phase. For the runtime phase, we have basically built security dashboards into Google Cloud Kubernetes Engine, so GKE and Cloud Run. And those dashboards, they have tools behind that are constantly scanning your workloads, your running workloads at runtime, and highlighting if you have issues there, like vulnerabilities, but also misconfigurations, right? And I'm not going to go too much into details with binary authorization, but essentially this is how we think a software supply chain, a secured software supply chain security could look like. Essentially, starting from the development phase, instead of using your local laptop or cloning code to your local laptop or computer, you use a cloud-based workstation and you do all your development in the cloud, right? Then you use Cloud Build to do the build part, and Cloud Build is Salsa 3 compliant, so Salsa level 3 compliant. I'm going to show you later that. Then once your images are built, you store them somewhere, and in that place you store them, in our case, in Artifact Registry, we have continuous container analysis, automatic continuous container analysis, right? And then at deployment phase, you also have the same thing, and then at runtime, you have also continuous container analysis, but also continuous misconfiguration analysis. And I'm going to show you an example. So starting with, let me see. Yeah, starting with, I have a very simple app. It's a microservices-based app. I'm going to show you how it looks like, actually. Hold on a second. Yeah, here we go. So this is existing app, which contains multiple microservices. It has a front end, and then it has a bunch of backends. I have already deployed all of this stuff into GKE. So I'm going to show you the runtime security now. And then I'll walk you through what a typical developer workflow would look like with the software delivery shield. So let's start with the supply chain, the security part. So here we have, if you are using Google Cloud and you are using Kubernetes Engine, we have added this thing called a security posture. And under the security posture, you can already see a dashboard which shows all the concerns. I can see I have like 3 critical vulnerabilities, 10 high, 9 medium, and 15 unspecified. I have some misconfiguration and vulnerabilities, and I have how many clusters are affected, right? And how many workloads are affected. So if I go to concerns, I can actually filter on those. So I can say, okay, give me all the critical vulnerabilities. And I can see here, I have a critical vulnerability on a library. And if I click on that library, I can already go to affected workloads, and it tells me exactly which workloads are using that affected library. And here, it tells me some recommended actions. So it gives me some links to details about what the vulnerability is and potentially how to fix it. This allows you to basically directly from the console see and get like an assess for yourself whether you want to implement this fix or not. But I can also get other stuff like misconfiguration. So if I click on configuration, I see here I have a container which runs privileged, which allows privilege escalation. This is a very common misconfiguration in Kubernetes, especially on Docker, is you allow a container to escalate its privileges, which means if somebody would hack your container, they can just escalate their own privileges and potentially do a container escape, right? And then here again, it gives you like recommendations. It says open your YAML file for the affected workload and add those fields here, right? Now, let me show you how the the workstation stuff looks like. So I will go here into my workstations. Yeah. So I've already created a couple of workstations. One of them is actually IntelliJ based. So it uses the IntelliJ IDE. The other ones are just regular, so the base IDE, which is the open source one. So I have already launched one here, which I'm going to show you. Let me show you one thing. So I have just a standard, no, I don't want the policy part. I want code. Show me code. Let's say static or templates. Yeah, I have just a very basic front end here, which has like, HTML, and you can see this looks and feels like Visual Code IDE. I hope it's visible in the console. It has built-in source control. It has a bunch of it has Cloud Code built in. I told you earlier. Um, it also has like extensions. You can deploy extensions, or it has a bunch of pre-deployed extensions in it. So essentially, it just looks and feels like Visual Code, right? Which you are probably already familiar with. It does have built-in emulators for some of our software. So if you're using PubSub, if you're using storage, if you're using Cloud Run, it does have built-in emulators. Unfortunately, I was trying earlier to use it, but it failed. I don't know why. But just to demo that I'm not like bullshitting you here, this is a Linux-based station. It's a Linux-based workstation, right? So you are effectively essentially SSHing into a VM in the cloud, and you have a beautiful GUI that you can use to develop, right? Now, it does come with some limitations. For one of them, for example, is you cannot do Android development and push into like a local phone, so you cannot do that. But probably with the JetBrains gateway I showed earlier, that would not be a problem. So then I can maybe do some modifications and show you how the rest of the stuff looks like. But let's say here, hello cloud app developers. I'm just going to do a very quick change here. And let's see, do I have my changes? Gate status. Yep, but I don't want those. So I'm just going to revoke, restore this one. Boom, and I want only one file. Okay, cool. So I have the modifications to one file, and I'm gonna commit those changes and show you what the rest of the supply chain could look like. You can do it from the command line. I like to do it from the console. I can do this is a commit message because I'm too lazy, and I still feel like Git. Git kind of what? No, come on. Make sure you configure. Yeah, okay. Git log, whatever. Okay. Okay, sorry about that. I'm just gonna do that right now, and let's see. Come on. Okay, cool. Sync changes. Boom. Right. So I'm pushing code, right, as usual. And now one thing I have here is I have a CI pipeline. Again, even if you're not used to cloud build, that's totally fine. You can think about it as a CI pipeline. So there is a cloud build YAML file, which describes a bunch of steps that needs to happen. One of them is just Docker build. And the second one is triggering the CD pipeline. So let me show you how my CI pipeline looks like. This is Google Cloud Build, which is a CI. It's a managed CI. You can see that already there is a build which was triggered. I can click on the build, and I will see that it has two steps. One is the Docker build, and one is triggering the CD pipeline. I'm not going to wait for it to start or to finish, but effectively after this, or actually I can show you a previous build. So I can look at this previous build here, and I can see already in the build artifact, this is my image that was built. And if I click here on the security insights, I can look how many vulnerabilities this container has. And I can also look at this thing called provenance. So provenance is part of the SALSA level 3 compliance requirements, which essentially says that when a build pipeline builds an image, it has to attach some metadata to say how that image have been built. And so this essentially are the metadata that tells us how the image was built. What are the steps that have been followed? What are the arguments? When was it built? What was the outcome of the build? And which configuration have built it? Which revision ID? Which commit SHA? Blah blah, bunch of things, right? This is essentially, you can think about this as the recipe, and the Docker file in my case is the ingredient. So the Docker file is the list of steps that the build pipeline has to follow to build the image, and these are the recipes. These are the actual step-by-step instructions that have been followed to build the image. And so this is added automatically here. Then one other thing I have is, I can show you this in here. I have a CD pipeline. Again, using Google Cloud Deploy, don't worry about it if you don't know what it is. It's a CD pipeline which has multiple stages. In my case, I have a diff stage, I have a stage, and I have a prod stage. And essentially what I do is whenever I build a pipeline, I just deploy whatever I built. So the artifact, if it was built successfully, I deploy to dev, and then I can promote it to stage and promote it to prod. I can show you how that looks like. I think it's here. Yeah, this is my pipeline. And it's just a simple pipeline that has 3 stages: build, dev to stage, stage to prod. The only difference here is that stage to prod has a manual approval step. So there is ways where you can assign certain people. Typically, a release engineer, you can assign a release engineer permission, and that release engineer has to go and look at what have been deployed to stage, check that it's good before allowing it to progress to production, right? Not spending too much time here because this is, again, Google specific stuff, but just showing you the overall idea. Again, I can go to like a release and I can look at the artifact. I can click on the artifact here, for example, and this will take me to where that image is stored. And I can look at things like versions, but I can also look at, hold on a second. Am I in the right one? No. So this is not the container image. This is not what I wanted to show you. Sorry about that. This is the source, actually. This is the image, right? But why does it show me? It doesn't give me a clickable link. Okay, whatever. I wanted to show you that it has also a built-in security dashboard, but I don't seem to know what it is. Okay, sorry about that. Anyway, it does. It exists somewhere. I just forgot where it is. Then my runtime, in my case, I'm running stuff on Cloud Run. Could be anything. We have also built in security dashboard here. I can go and look at a specific revision, and I can look at security, and it tells me how this image was built. And I can look at the provenance, which I showed you earlier. I can look at everything I have showed you before. Essentially, the TLDR to all of this is, and I'm actually gonna stop here because I think I'm at the 45 minutes mark, is that we can secure the supply chain from development all the way until production, provide security visibility across the entire chain, make sure that people know what they are pulling images from, dependencies from, make sure that whenever they build stuff, they are building them properly using the rights dependencies, and that the stuff they write are also vulnerability free, and also having this visibility across the entire chain. Because all I showed you today are typically not the kind of things a single person do. Typically, software, when it goes from developer to production, is touched by at least 2-3 teams. You have your developers, and you have your QA people, and you have your maybe testing people, and you have your DevOps people, etc., etc. And if you are able to get that information across to every single step, then you can ensure that your software is as vulnerability free as possible. Nothing, of course, is vulnerability free, but as vulnerability free as possible all the way until it gets to production. And that's it. That concludes the end of my talk. I hope it was useful, and I am open for questions. All right, there was one question that says, do you have a way to revoke the signed image because vulnerability is found later after it's signed? Yes, John, you can change the key, essentially. In our case, what you would do is you would unpromote so KMS itself, key management system, which is what I used for signing, has a concept of versions. So you can create a new version of the key. You can sign the images using new version of the key, and then you can change the policy to say, okay, now you have to check against the new version of the key, which means all the images that have been signed using the old version will not be able to be deployed. So that's how we do it typically. From Danielle, which do you think is the most emergent attack vector that we will see in 2023? Very good question. I think that one of the main ones I see bubbling quite a lot is actually trying to social engineer toward developers and support folks. So by getting your developers, or especially your support people, because that's actually a thing that again people are realizing now. Sometimes inside some companies, you might have DevOps team or support team or production teams or platform teams or whatever name you want to call them. Basically, those that operate the system, not those that build it. You would try to social engineer toward those, and you try to get them to click on links so they can leak some credentials or something. And so that was the case of that managed CI tool I talked about earlier. I don't want to mention the name, but this managed CI tool, the attack was carried toward a support engineer, which has access to certain parts of the system, and they manage to get the credentials of that support engineer, and that's how they manage to compromise the system. So attacking people essentially is, I think that social engineering is not a new concept, but social engineering targeting specific teams is gonna be a thing this year.
Well, that was a great talk, Abdel. And just to confirm, as some people have also asked, we are going to send all the registered attendees the slides of the presentations that you did and a recap of the event with links to the talk, and also for those who couldn't make it live, the recording itself. Just wanted to thank you so much for your time. We really look forward to seeing you soon again, and we hope to continue to enjoy your Kubernetes podcast. That we encourage everybody who don't know it or haven't heard of it to look for it at kubernetespodcast.com. But again, all this information will be sent to all the community.
Thank you very much, Steve.
Thank you,
folks.
Thank you. Bye-bye. Bye-bye. Okay, and now we'd like to introduce our second speaker. Hello, Alessandro. Can you hear us?
Yes, of course. I can hear you.
Hi, Alessandro.
Hi.
Alessandro, everybody, is Alessandro Vozza. He's a DevRel at Solid.io. He's a community leader and CNCF ambassador, and he also organizes KCD Amsterdam. And just wanted to thank you so much for joining us today, Alessandro. For all those who don't know it, he's joining us from the US, so I imagine it's early morning for you.
It's noon, actually.
It's noon already. Okay, excellent. Well, Alessandro, I don't want to take any more of your time. We're just slightly gone over your slots, so I'll leave you to it so you can start your presentation.
I'll keep it brief and short, and I'm very glad to be here and share the stage with you and with Abdel. And it's interesting, very interesting talk. It's also one of my interests, secure supply chain, and about the possible attack vector and the social vector attack. Like, so they're gonna be very, very much more sophisticated with all the chat GPT. Imagine AI talking to a support engineer and just trying to figure out passwords. Is gonna be dangerous but interesting time. And they'll shed some light on how to.
Yeah, we completely agree. Well, Alessandro, I'll leave you to it so you can start sharing your presentation as well.
Yes. So I think I'm gonna share the whole screen, right? Entire screen will be fine, because I'm probably gonna also have a demo soon enough. Okay, let's all right. So thank you for having me. I'm just temporarily in US for this week. I'm coming back soon. I got this invitation, and I got this new role at Solo.io, where actually we are not developer advocates per se, because we realize that developers are, of course, like very important, and we love developers. I was one, of course, but my role is platform advocate, because our focus is really around platform engineers and providing the tools for platform engineering, which is up and coming, is on the rise, right? So we want to give them the tools to build awesome platforms, of course, on the platform architecture du jour, which of course is Kubernetes, but also we provide service mesh, and we're gonna talk about a lot of stuff in the coming 30-40 minutes. So about me, this is one thing that you need to know about me. I really love communities. I've been running the Dutch Kubernetes Meetup for 7 years now, 3,200 members almost, and next week we are actually culminating the efforts of about 3 years, really, because we did it in 2019. It was so successful. We wanted to come back in 2020, and we had to put our dream of having like a large community conference in Amsterdam on ice for 3 years. And so finally everything is coming together. And so if you want to join, please reach out. And if you are in Amsterdam or around Amsterdam or the Netherlands, reach out. I'll be happy to discuss every possibility to engage with the community. So I am very lucky to be now for 2 months now working at Solo.io, which means that I get to see how the pizza is done, right? So or or the pasta or whatever. We are very close to the service mesh world, right? So Solo.io actually has leadership, thought leadership, but also actual community leadership in many of the communities around service mesh, specifically Istio. So we serve customers, we serve communities, we serve the open source world by providing the best breed of service mesh. So Solo.io, I'm not going to talk about it a lot about what we do, but please reach out. We have also, at the end, I'm going to show you how to learn these things for free in our academy. It's pretty cool. We have a bunch of customers, and we are growing so fast. And because the market is growing, this service mesh thing is started pretty slow, but people are realizing, companies are realizing that, as the previous talk was highlighting, it's a bad word out there, right? So you need to smart up, you need to be smarter than the attackers, and you need to implement concepts and ideas that are up to the cloud native world and to the world we live in, which is full of bad actors. So things like zero trust and application networking, they are all core to our business. So, and some of them we'll discuss it today as well. So we found that we are a great company to work for. That's why I joined, and I really love it so far. But anyway, so service mesh. So I realized when I give this talk today, I have a bit more time, so I would like to introduce what is a service mesh, because it's maybe not on everybody's plate, right? So for us, of course, we work on this day in, day out, and it's just a given. Lately I opened my talk to say that I'm on a mission to install a service mesh on every cluster, right? So that's because I believe service mesh is a good and it's kind of inevitable add-on to every Kubernetes cluster. So a service mesh the idea of a service mesh was born a few years ago, especially when the cloud native paradigm ideas came to life, and people were really realizing that, yes, it's great, we got this distributed microservices and they work just fine, but what about observability? What about security? What about managing and understanding the relationship between these services and how they communicate? So communication between microservices specifically exploded, because of course now you go from one monolith, doesn't need to talk to anybody, or maybe to a database, to a distributed architecture where multiple services talk to each other, and you need to abstract the networking part. You cannot just rely on the application to be smart enough to perform all the functions that you need. For example, like mutual TLS termination or collecting the metrics and the traces. You cannot rely on the application, so you need something else, right? So this is why service mesh as an idea came to life. And of course, so these are the things that you have, the challenges that you find yourself in when you start to expand and to have like a microservice architecture. So you want to do smart networking. It's not just pipes, right? So these two services are not just connected by a dumb pipe, but you want that pipe to do something that serves a business purpose. So circuit breaking, retries, timeouts, they're all very important features of the service mesh. So and also you want to manage them in a smarter way. You just don't want to just delegate to the teams, to the developer teams, the management of this, like mesh of services, but you want to centralize the management. So that's is another very important part of what a service mesh can bring to the table in value for your organization. So what about we intercept the traffic between the two services and this is the whole point of the talk, like there's the classical way to do service meshes with these proxies, right? So historically embedded in your application. I mean, not embedded, but very close to your application. It's in the Kubernetes world, there's a concept of a pod, and the pod contains can contain multiple containers, and the proxy becomes one of the containers included in the pod, right? And this is the classic sidecar model. So once you have these proxies that do the egress and ingress to your application, so all traffic is routed through the proxies, then you really have control of what can go on and what can be allowed in and out of our application, and you can measure, of course, you know exactly how many requests are falling, how many requests are ending up with 200, 400, or 500. So it's this idea of sidecar proxies enable kind of the revolution of service mesh, kind of the advent of service mesh and the adoption, which was limited in a way. I mean, of course, like not every organization out there already used service mesh, but and we will discuss why, maybe one reason why this is not happening and one possible fix and solution. So these are the functions, the business function really that through technical, of course, implementation, the service mesh performs for you. You can do anything from, of course, like a traffic shaping, quality of service. You can ensure that you give enough, for example, in measuring requests per second or bandwidth or anything else to your application. So traffic shaping, traffic control, you can prevent some application to reach other application. The sky is the limit, quite literally. You can ban the communication between your applications to your will. Not only by service discovery, load balancing, and very importantly, because the service mesh is there, it's like the gatekeeper to your application. You can use the proxy to do what we call layer 7 policy enforcement. What do we mean by that is you can make a decision for every request, maybe authenticating the request with an external authentication system, or make sure that only certain parts of your API, so making a path-based decision. So if you hit a specific endpoint, you get a list, a policy applied, and if you hit another endpoint, there's another policy that can be applied. So you can make sure that, for example, some of your clients can reach the get, can use the get HTTP verb, while other clients can instead access the same API endpoint, but through the put, right? So you can decide which service can write and which service can just read. So it's a whole plethora of functions that are quite compelling. And once you discover the service mesh, then you really think, why I didn't use it before, right? So it's the kind of thing like that you just have the eureka moment and kind of like really you sure there's some price to pay. We will discuss it, but definitely the advantages are outweighing the disadvantages. So now in this service mesh arena, of course, there is not only one product or one project. There are many. We're not going to cover everything today, especially because I have interest, of course. Like I chose my battle, right? So, and Istio is definitely the king, the 900-pound gorilla of the service mesh in a way. It's been one of the oldest, one of the first to implement these ideas. And it's an open source project, of course. It started at Google, pretty much like Kubernetes, right? So it was donated. There was a governance structure built around it. But then what happened is that very recently, at the end of 2022, Istio was donated to the CNCF. Now, if you know me, you know that I really like the Cloud Native Computing Foundation. I used to be a CNCF ambassador. For me, like being part of the CNCF for a project means kind of you made it, right? So if a project is part of CNCF, means that there is some assurance on the quality, on the governance. It's a big house for a lot of open source projects that kind of makes sense to donate your project to CNCF, because then you're joining a big organization, big foundation that can promote you, can give you, like help in governing and growing your project. So at the end of 2022, Istio was donated, so it's now a fully incubated CNCF project. And even recently, more recently, Istio applied for graduation, which means in CNCF you have several levels of projects. You start as a like experimental project, and then you graduate to incubation. Incubation means that it's not exactly production ready, or they're still growing, and then you can reach the final stage, which is graduation. And of course, like projects like Kubernetes, Prometheus, Envoy, those are graduated projects. It means that definitely the community is there, that the project is mature, been going through several security, also security assessment, and definitely Istio is part of that. And Istio did apply for graduation, which will make the one of the projects that so quickly went from incubation to graduation, because of course it's been around for already a few years. So, and in September last year, a new way of deploying Istio, which is the today's topic, was launched, which is the ambient mesh, and we're going to talk about it. So this is the basic architecture of a service mesh. In this case, Istio. It's not going to be very different for other service mesh on the market, or other project out there. It's really based on the sidecar proxy idea, right? So sidecar is a pattern in distributed applications in general, but especially very popular in Kubernetes. So you got these sidecar proxies sitting next to your application all the time, and they kind of hijack the traffic. So you can manipulate the traffic in and out. Now the problem is, and let me just check if everything is fine. Yes, everything is fine. So, sometimes because I don't have any feedback, I don't have any other screen, I just have my laptop. So I was wondering if maybe I was just talking to myself for half an hour. No. So the sidecar proxy, they sit there and they do what they are supposed to do, proxying your traffic. But of course, like if you have a proxy for every pod or application, then configuration is a problem, right? So you need a way to distribute configuration and update those configurations at scale to every proxy. And that's where Istio comes in. Istio is really like the control plane for sidecar proxies for the service mesh, which is based on Envoy. So the proxies itself is another open source project, CNCF project called Envoy. So it's very efficient proxy, born for this purpose, like proxying traffic in and out of your application. So an Istio-D is the component that collects your wishes, your desired configuration, right? So because we are in cloud native, so we do love declarative configuration. So you declare your configuration through Kubernetes objects like CRDs of various kinds, of course, like gateways and virtual services and so on. Istio-D translate those declaration of intent, those CRDs, or those APIs, into Envoy configuration down to the proxy, and distributes them through very efficient mechanism. It's the XDS discovery protocol of Envoy, which we're not gonna talk about much, but that's how it works in general. Like, so this is more or less what you will see in every service mesh. Now, what is the problem here? And this picture is not mine, of course. It's from Jimmy Song. It's a very popular depiction of what is that this proxy does into a pod. So the proxy is injected in the pod, so it's not too difficult, right? So in Kubernetes, you have this admission controllers, right? So Istio works by injecting an extra container into all the pods that need it. So the pods, for example, that are spun up in a namespace that has a specific annotation that marks that namespace to be managed by Istio. Literally, the admission controller adds this little piece of YAML to every pod that adds the Envoy proxy. So the Envoy proxy also is an init container that programs the IP table route. So it's a bit complicated, but in general it works like this. So there's an init container that reprograms the IP tables in the namespace of the pod, the network namespace, right? So every pod lives in its own network namespace. Is a concept in Linux that isolates the networking specific to a process, in this case the application container. So all the inbound and outbound traffic is forced to go through the sidecar proxy, through Envoy. So it works. It's a bit complicated to get your head around it. It's don't worry if you see too. I mean, if it's too complicated, but it works, right? So it's nothing scary or anything. Just that's the way the sidecar proxy works. But now think about it. So every pod requires injection, so requires a proxy to be injected, requires restart, because pods you cannot inject a container on a pod on the fly. You need to restart the pod, right? So you need to actually recreate the whole network namespace, and it's non-destructive for sure operation, but it's a bit heavy, right? So you have to do this injection. I mean, you have to mark a namespace with this annotation, and then the Kubernetes does the rest. But still, now you have running not only your application but also a sidecar next to it. So at scale, this could be something that you may find annoying, or more than annoying, actually impacting your wallet. Not only you are running more stuff, more processes, so one Envoy proxy per pod. What about security, right? So now you have, of course, you have a bigger attack surface because you literally running more stuff, more things. So it could be tricky to evaluate also the impact of a CVE discovered in Envoy or somewhere else, how that can affect your security. What if your application can access the proxy and then see the configuration? It's a pretty tricky way to it opens up for consideration about security, performance, and this actually is probably one of the maybe misconception, but also definitely a reason of that slows adoption of service mesh, right? So this heaviness of running so much more processes in your cluster than just pure application will probably, I heard from customers and people that it's probably something that slows down a bit the adoption. So what if you can just rethink the whole thing, right? So what if you can see what you can do better, given all the pieces that you already have, Istio, Envoy, and how to rearrange things in a way that is better for your wallet, so cost reduction, more simple to think, to reason about, and also better security posture and improved performance. So that's where the idea of Sidecarless, which is not a new Linkerd started Sidecarless, and it was abandoned later, and then but you can reason about why this makes sense, and for us it does make sense, and for us as Solo, it does represent the direction that Service Mesh is taking. So, and we investing heavily in the community first, of course. So we contribute to the community version, of course, to the NBM Mesh in Istio community, and of course also working on integrating this in our product, because we want to bring it to all customers in an enterprise way, right? So what is NBM Mesh? So imagine that if you can replace all the proxies with one per node proxy. It does exactly the same thing. So it takes the traffic out of application. Now, instead of going through their own natural route, which will normally an application running a pod will send traffic through the Linux kernel, and the Linux kernel will make a decision to send it somewhere, right? So to send it probably to the next hop. Now, if you hijack those applications traffic and you run it through a proxy that runs on the node itself, then you achieve the same thing. You can have exactly the same feature set of a classic service mesh with way less cost in terms of course, like on computing, but also in complexity, right? So exactly the same. So what is there not to like, right? So you get everything that a service mesh promise you with less trouble, right? So especially one thing that it really strike me is that your application is really oblivious to the fact that it's part of a mesh. So the application doesn't need to know anything. Your pod manifests are the same. The application keeps working, so you don't need to restart anything. You just deploy this proxy per node that gets the traffic and makes the magic happen, right? So that's one of the big advantages. So less complexity, less impact on your running application, so business continuity, and so on and so forth. So it's probably, there are arguments pro and cons, of course, like because of course now all the traffic is managed by one proxy per node instead of multiple proxies. So you may think there is some impact on security posture, but trust me, there are many reasons why this is better. So there are discussions, of course. It's probably not enough time today, but it's an interesting idea, and it's actually working pretty well. So you still have the same security posture. So you have the proxy is Envoy, right? So it's being rewritten today with Rust because I'll explain why in a second, but it's actually the same proxy that you inject into every application. You can just run it on the node and let it do the job. So also one reason that this is better and this approach reduce cost and complexity is this. So the proxy injected in the node, the sidecar proxy, has to do both layer 4 and layer 7 calculation, layer 4 and layer 7 routing, right? So what does it mean? So both the decision based on pure IPs, right? So layer 4, so the TCP IP layer, if you remember the OCI layer, so has to be done by Envoy. Envoy is a very, very efficient proxy for this, of course. But also the layer 7, which are the more high-level decisions, like route-based traffic decisions, or compared to, for example, layer 4, for example, is mutual TLS termination, while layer 7 is circuit breaking or traffic shaping, or make sure that 1 in every 10 requests are dropped, right? So rate limiting. These kind of things are layer 7, while the more basic networking stuff is layer 4. So the same proxy has to do both, but not every application needs a layer 7 processing. So by splitting the layer 4 into the per node proxy and the layer 7 processing into its own proxy, which is not deployed per node, but it's deployed per application that needs it. Today is deployed per service account, which is more or less identified with the SPIFFE identity, but we'll talk about it. But so So the idea is that because you split a layer 4 and layer 7, every proxy is very specialized. So the layer 4 proxy on the node does only layer 4, and the layer 7 does only layer 7 for that application. So very specific to the application. So that's one way to solve the problem of sidecars. So we believe this is something that really will be prominent, the prominent way to deploy service mesh in the future. Don't take my word for it. Just keep an eye on it. But the way we also have in, we'll talk about the where you can learn more, of course. So this is also the impact on your wallet. I'm gonna speed it up a bit because I think we're gonna end by the end of the hour. So this is how it works with sidecars. Just repeating what we discussed before. And this is what we call the layer 4 proxy component. We call it Z tunnel. So the Z tunnel sits on every node and establish a multiplexed connection between the Z tunnels. So, and inside that connection, it's called HBONE, HTTP base overlay network encapsulation. So that's an acronym that I'll explain later. So there's the application doesn't need to do anything special. It just delegates to the Z tunnel everything that needs to be done for communicating with other service mesh based application, and also non-service mesh. So the Z tunnel can communicate with other nodes that don't run, or that you can also communicate with applications that are not part of the mesh in the same way, transparently, from the fact that your application is either onboarded or not on the service mesh, which makes it onboarding much easier. You can have a mix, and you can slowly adopt service mesh and onboard application on your mesh at your own pace. So you don't need to the application in and out of the mesh. You don't really care. They all can talk to each other. So, and these are all the features that you learn to love in service mesh, just replicated without the burden of sidecars into every pod. So that's how it works. Of course, like Istio is still there. Istio programs instead of sidecars. Now Istio programs and configures the tunnels. These are daemon sets running on every node, and they establish this HTTP connect tunnel between themselves. So that's it's pretty straightforward. So in this case, also for if a new node comes up, for example, of course there's a new Z tunnel coming in, and the pod running the tunnel will reach out to the Istio daemon, Istio server, so the Istio management plane for configuration. And then we'll establish communication between the other Z tunnel, all via TLS, all mutual TLS. So the TLS is, of course, like the certificates are provided by IstioD through various mechanisms. Of course, like you can have an external certificate authority, you can use the built-in, but in general, like IstioD is the one responsible for providing these identities and these certificates and rotating them to every Z tunnel. So, and this is for pure layer 4 communication. So your application, you didn't implement any layer 7 policy, great. Your traffic is encrypted by default because the tunnels are encrypted via mutual TLS, and nothing else happens, right? So there's purely a layer 4 communication between your application through the Z tunnel. But what if you do want to be a bit more sophisticated and then actually implement layer 7? Then you deploy what we call a gateway, which results in a gateway as a object in Kubernetes called a gateway, is part of the gateway API, that results into a new pod created, a waypoint proxy, runs in your cluster, runs one per application, of course, and that proxy will get the traffic from the Z tunnel, apply the policies that you want, and then forward the traffic to the Z tunnel of the receiving end of your communication, of your networking. So if app A wants to talk to app D, and there is a policy in place on app D, then app D will have a waypoint proxy which will make a decision based on the policy itself, and will go from there. So notice here that we're also depicting the CNI. We're going to talk, if we have just a few minutes, this HBone. So just quickly, so you don't need to have individual connection, but the HBone multiplexes multiple connection from different applications into one single tunnel, and so it's more efficient. And that's why I think we think you can achieve better performance, because the communication is not between individual sidecars, but it's kind of aggregated into this tunnels. I'm gonna skip the live demo, but I'll give you I'll give you later, because I want to talk about eBPF. So eBPF, of course, if you don't know what it is, it's a way to inject or to graciously ask the kernel to execute some code for you. Of course, the kernel is the most important part of every Linux OS. Of course, if you crash the kernel, it's game over, right? So the whole machine is down. So rightly so, the Linux kernel is very protective in what can execute and what should execute. But this, of course, limits a bit what application user space can do, because sometimes you need to interact with the kernel level primitives like the packet filter or the network interface, or to interact more closely with the file system. So the BPF, the Berkeley Packet Filter, was born a long time ago to do exactly this thing, like executing network programs, specifically network, and then it's been extended to anything beyond the just networking, also to monitor anything running on the kernel level. So it's a way to give or to ask the kernel to execute little programs verified by the kernel that can execute in the kernel, so getting access to low-level things running in the kernel, like, for example, as I say, like network counters and stuff. And then the result can be sent back to the process calling for it. So it's a very powerful idea, very powerful mechanism that can execute small programs. So that's the crucial part here, right? So BPF programs are safe, and because they are safe, they usually cannot be very sophisticated, but they work extremely well, extremely fast, because they are executed in the kernel, so there's no context switching. So a lot of CNIs, the container network interfaces in Kubernetes, are actually relying on the BPF, most notably Silu, which is what we also as Solo use as a foundation for the service mesh. So when you get these things like this is how it works, right? So this is you can be very creative with what you can do with eBPF. You can profile and trace and collect metrics and make sure, and there are startups out there and companies out there that leverage eBPF for all the crazy stuff, including, for example, like for security. So you can really you can be alerted when a file is modified, or when there's an access, when somebody elevates privileges, right? So all these things are possible to be collected by eBPF programs and then sent to the user space, where you can reason about it, like collect it, send it to Prometheus, do something interesting with it. So what about? So we show you, we discuss it. So there is a layer of redirection. There's a reprogram of IP tables within the pod. So what if, and this is very low level, right? So in this, of course, IP tables is it's been around forever as well. But what if you can replace that with eBPF? So eBPF is not meant to replace the service mesh, but it's meant to help the service mesh be be faster, be more safe, and more flexible. So the idea here is that BPF plays a role in this. So that's why the title of the talk is the future of service mesh, Sidecarless, eBPF. Why not both? Why not using everything at your disposal for to accelerate adoption, to make it better, right? So in this case, eBPF cannot implement sophisticated functions like layer 7 policy or anything that is really that requires a proxy, but can do things like make sure that your packets are sent to the right place. In this case, the proxy. It works either way. So Sidecar or Sidecarless, eBPF doesn't really make a distinction about it, as long as you use it to the kernel is modern and supports eBPF, then you can use it for your needs. And that's why we call this accelerated networking in service mesh, because we don't rely anymore on the IP tables, or we rely on eBPF and the CNI based on eBPF like Cilium to accelerate the traffic between the application and the proxy. So this is basically what you see in the OCI layer. There's another layer depicted here, which is the GraphQL, which is really like built on top of layer 7. So when you aggregate multiple APIs, multiple layer 7 calls into a consistent logical view, which is GraphQL, which we may talk about another time. But so, and eBPF sits right there, and the layer 4, layer 3, where you can really do what is meant for, which is executing this fast but small and dedicated programs for example, reprogramming the networking within a Linux host. So that's where you can learn more. Solo Academy, academy.solo.io. It's where we put all our workshop. There's a workshop on ambient mesh. I had a demo. I'm gonna just give you the link to the GitHub repository, which was developed by also a former colleague from mine. We gave this talk before. This is our public Slack, so you can come there and discuss and talk and ask questions. And finally, and I think we are almost at time, if you are in Amsterdam next week, please reach out, because it's going to be awesome. We sold almost all the 450 tickets, and we got a lot of workshops and talks and just a lot of good time with the Dutch community, including a vegan barbecue and a great party on Friday. So with this, I'll finally switch to I'll stop presenting. I don't see any question. Am I wrong? Oh, are you muted, or am I muted?
Can you hear me now?
Yes, I can hear you now. Yes.
Sorry about that, Alessandro. Yes, I just added to you as a banner just in case.
Yes, cloud managed Kubernetes and service mesh. Well, of course, there is some opinions there, right? So your managed Kubernetes may have already something opinionated that you can start with, but in general, there is not big hurdles in deploying service mesh on managed Kubernetes. Managed Kubernetes like AKS, EKS, they're really agnostic, right? So they have to be, because they can't possibly predict what their customer will use or want to use. So they keep it intentionally very open. They use vanilla Kubernetes. They give you choice to deploy what you like. So Istio works on every major managed Kubernetes. So there's really nothing preventing you from using it.
Excellent. Well, thank you, Alessandro, again for your time, for taking the time to join us, even though you're in a different time zone right now. Just to remind everybody, we will share the slides for your presentation, as well as some links that Alessandro would like to share with us in the community, and we'll be sharing this to the entire Cloud App developers community. Alessandro, thank you again so much. We wish you the best next week at Kubernetes KCD Amsterdam. I'm sure it's going to be a blast, and we look forward to seeing you at KubeCon very soon.
Yes, also, yeah, reach out, because KubeCon comes to Amsterdam and is a dream
Yes.
come true. Also waiting 3 years for this, but finally is happening. All right.
Excellent. Okay, thank you so much, Alessandro.
Thank you.
Okay, bye-bye, and bye, everybody.